So I thank you for coming. I'm Meng Xiao from Wuhan University. Actually, Wuhan, a brief introduction for Wuhan is in the very middle of China. So if you ever visit Beijing, Shanghai, or Guangzhou, you can go to Wuhan within 3 or 4 hours with the highway. So anytime if you are interested, you can contact me, and you are very welcome to visit our university. And actually, first I'd like to thank Alexei for the invitation that offer us the opportunity, offer me the opportunity to present our works, recent works about the, as you should say here. Oh, maybe I should. Okay. Oh, the nonlinear acceptance point. And here is brief. Here is the view of our university. Is actually is in the autumn and is also beautiful in the spring. So you're welcome to visit it once again. So okay. So this so first and first, I'd like to thank my group mates, Dr. Bai Kai Bai, Liang Fang, and Tian Rui, and Jia Zhen, and especially for Dr. Bai, who was my PhD student and now my postdoc. He contributed to almost all the modeling and simulation, and also the circuit experiment we will talk today. And also, I'd like to thank my colleagues, Professor Wang, Professor Liu, who is in our who are in our department, and Professor Fan. I guess some of you already know him. He's from Stanford University, and also the founding support of our university and national the NSFC and the National Key Research of Development Program of China. So here's the outline of this talk. I guess some of you guys are already quite familiar with the concept of the acceptance point. And so, and today I will talk about something about the nonlinear acceptance point. And so as a start point, I will give a brief introduction of the basic concept of acceptance point, as well as nonlinear acceptance point defined in our, what do we mean by nonlinear acceptance point? And later on, we'll talk about how to design an experiment, a very simple experiment within a circular system to show the basic features of the nonlinear acceptance point. And then I will talk about some nonlinear NEP-based applications, such as the sensing and chiral state transfer. So the first concept we need to talk today is about the acceptance point. And EPN, we mean that an order n acceptance point. So for that, we have n eigenvalues and their eigenvectors collapse into one. So the simplest case is EP2, which to construct an EP2, we need two cavities coupled together, and one is gain, one is loss. And here's the Hamiltonian, here's gain and loss, and here's the coupling. And within this simple 2x2 Hamiltonian, first, if we look at the eigenvalues, we will see that as we increase the gain or loss ratio, the real part of eigenvalue will come close to each other, and then at this acceptance point, they collapse into one point, and then after that, the imaginary part of the eigenvalue will split. And this point we will see later. We will show that actually it's different from the degeneracy, as we talk in the as we are familiar for the Hermitian case. For this acceptance point, there's only one eigenvectors. So for the degeneracy, the general degeneracy will have two eigenvectors. So sometimes we call it the defective point. And this feature can also be seen from the eigenvectors. So for Hermitian case, which means that there's low gain and low loss, these two eigenvectors are perpendicular to each other. And then as we gradually increase the gain or loss, and we'll see that these two eigenvectors become parallel to each other, and then this delta over kappa, the acceptance point here, they become the one eigenvector. and then this is the point. This is just the acceptance point, and then after that, the eigenvector was split once again. So the ideas about the acceptance point is quite simple. We only need to have two resonators or or more resonators for higher order acceptance point, and then we have gain and loss or non-reciprocal coupling. Then we can study the exceptional feature. So there are already a lot of platforms on which we can investigate the exceptional point and the physics associated with this. So here, for example, here's an acoustic cavity system. Acoustic cavity provides the resonant mode, and we can couple them together and then introduce noise. It's kind of difficult to introduce gain in this acoustic system, but we can have a bias loss again, which means that one is noise, one is more lossy. So for acoustic system, and here is a sample for the circular system. For circular system, we can use the LC resonator to construct a resonance, and then we couple them together through an inductor or capacitor. And also we can have the optical ring resonators as the resonator, and then couple them together, and also the waveguide and the fiber system. So as long as we can construct the resonator and then we couple them together, we introduce gain and loss or the non-reciprocal coupling, we can study the exceptional, the physics associated with the exceptional point. So it's quite general. So the physics discussed here is quite general. And there are a lot of novel phenomena and potential applications associated with this exceptional point. For example, we can have the vision of the missing dimension in this paper, as discussed in this paper, and we find that some of the exception points have hybrid topological environment, which means that the topological environment or the topological charge is different. Actually, depends on how we winding it. We winding it along one direction or the other direction. The topological charge is different. And also there is chiral state transfer and the enhanced sensing. We will talk about these two applications later. And so that's all for the this the introduction or the introduction for the acceptance point. And for nonlinear acceptance point, actually we only change compare with the linear one. We only introduce a saturation. Here as the first example, we only change the linear gain to a satural gain. A satural gain actually is quite later, as we can. The satural gain means that the gain coefficient is a function of the wave function inside this resonator. It decreases as a general. The gain coefficient decreases as we increase the wave function. The wave amplitude inside this resonator is quite later, as we can actually satural gain is quite later in physics, as you can imagine that the pumping which provided energy into the system is fixed. As the wave amplitude increase, the gain coefficient must be saturated, or there we will need infinite energy into the system. So actual gain actually can satural gain actually can introduce a lot of interesting physics, such as the topological laser talk in this paper, or the wireless energy transfer, which they use from Professor Fan's group. They use the satural gain to stabilize the mode. And they use this, and then they use the mode to transfer energy between two resonators. And then with this simple change of from the a linear gain to a satural gain, here we show the spectrum of the system. So instead of here we can see that here this red and this pink surface represent the stable mode, and this blue one represent the unstable mode. For unstable mode, we mean that a little bit of noise will change the system, which means that the state on this blue surface is not stable. A little bit noise or variation of the parameter will change the state. It will jump to the either this surface or this or the surface below. So if we look at this two surface, we'll see that if we look at the surface of the eigenspectrum, we'll see that this red surface and this blue surface merge. We will later show that it's actually very similar to the excitation point. So we call it excitation arcs. And excitation arcs, which means an arc of excitation point. So this yellow point are all excitation point, and they form an arc. And we can say these two arcs merge to this point, which is an exceptional nexus according to the definition inside this paper. Exceptional nexus is actually a higher order excitation point, which requires 3 modes. So first we look at the eigenspectrum of this system. We see that we start from the low loss case, which we will have this S curve. And we see that, and here besides the real part of eigenspectrum, we also plot the imagined part of eigenspectrum. We'll see that here this red and this blue curve merge at this point, and then when we further decrease, we will further change the determining. We'll see that then the imagined part will emerge very similar to the excitation point, to the linear excitation point of order 2. And then if we look at the slope of eigenvalue, we'll see that the slope is 1/2. And also if we look at this point along the other direction, the slope is also 1/2. So if we only look at the eigenspectrum, they are almost the same as the excitation point in a linear system. And then for this excitation nexus, actually these two yellow points merge to this one. And if we look at the slope of the eigenspectrum is 1/3, and along the other direction is 1/2. This is one of the reasons they call it hybrid. They say that this exception nexus possess a hybrid topological invariant. So so after we have this the feature of the eigenspectrum, we'll see that actually we ask the question that in our system we only have 2 resonators. However, we seem to observe a feature which is unique, which is only possible for a 3-resonator system. So there are hidden dimensions in our system. So to answer this question, we need to do a mapping between a 2-resonator system to a 3-resonator system. So our idea is quite simple. We say that these two, we imagine that there is one hidden resonators. We cannot see it, and then we ask ourselves the question that if we can we extend this eigenvector to from a 2-element to a 3-element, and then decide this element the complex amplitude uniquely. The answer is yes. We know that for a linear system, this 3 eigenvectors should be normalized and by a circle, which together will give us 6 equations. And here we have 3 unknown complex amplitude, which is also 6 unknowns. So 6 equations and 6 unknowns. So we can have a 1-to-1 correspondence between this 2 resonator, 2 nonlinear resonator, and this 3 resonators. And then with this, then we can define the topological charge inside this linear system. Say we can calculate the phase rigidity, and according to this paper, the phase rigidity actually reflects the topological charge of the system. So here 1/2 means that the charge is 1/2, and here slope here the slope is a critical behavior of the phase rigidity. 1/3 and 1/2 means the charge is 1/2 if I remember it correctly, is one third along one direction and 1/2 along the other direction. So this is, according to this paper, is a hybrid topological invariant for this exceptional nexus. So so actually, up to this point, we can already say that actually this nonlinearity not only shifts the frequency of the exception point, it also changed the topology of the system fundamentally from a 2 resonators, from a 2 modes to a 3 modes, which is the reason why we can have a higher order exception point. And then it comes the first step. The dimension extension give us the first advantage of our nonlinear exception point. I remember once when I read this paper, we say that this is a very famous paper talk about how to realize EP3 inside a traditional optical system. Actually, it used a lot of it try really hard to realize, to turn the parameter to realize the EP3. The idea can be imagined from this toy Hamiltonian. We say that for inside this 3 resonator system, we have, this is the Hamiltonian to describe the system. And here a global frequency shift is invariant, so we can set omega 1 to 0. And kappa 1 can be used as a reference unit. So we can also set kappa 1 to 1. And then beside these 2 parameters, we still have omega 2, omega 3, gamma 1, gamma 2, gamma 3, and kappa 2. We need to turn these 6 parameters together inside which is a very large parameter space, and we want to find EP3, which is a very sensitive point. So the experiment, we need to put in a lot of effort in order to find this point. However, if we look at the nonlinear, also EP3, nonlinear EP3 inside our system, for the same reason, omega A is invariant, kappa is invariant, and here this gain coefficient is also because it can be turned automatically with this phi A. So in the real experiment, we only need to turn 2 parameters, which here the omega B and the loss ratio. So that's why we show here is actually the EX point can be found in a two-dimensional parameter space. So it's much easier to find an NEP3. So as we know that the effort need to find an EP3 is much less than the previous case. So we want to do experimental demonstration in our group ourselves. So as we already said before, there are a lot of platforms, and inside we start with the simplest case, which is we think is a circular system. So here's the circular diagram. Here is the typical LC resonator with a resistor. Resistor is a loss, and we couple them together with a capacitor. Here's another LC resonator together with a lective resistor, which is a gain coefficient. This gain is realized actually with this amplifier. And besides that, we also introduce this 2-dot component in order to turn the gain coefficient. So here's our experimental setup. It's quite simple. We have the oscilloscope to measure the wave function. We have DC power to supply power for the amplifier, and we have the waveform generator to control. Later we'll show that we have a bistable state. We need the waveform generator to select the modes we need. And here is the PCB board, on which we plot the circular diagram, and here's the circular element, the amplifier and capacitor, and so on and so forth. And also to turn the resonant frequency, which is the determining of our toy Hamiltonian, we introduce a homemade variable inductor. It's quite simple. We just 3D print this here, the helix and the hexagonal knob, and we turn this knob to increase or decrease the distance. With this, we can measure the inductance of this homemade inductor as a function of distance. It's a monotonic function, so it's quite smooth, which means that there is a one-to-one correspondence between the distance and the inductance of this inductor. So we'll have all the parameters to turn as required by the toy Hamiltonian. And for the bistable state, as we show here, the S curve will correspond to a bistable state. We need to select this state or this state. So what we do is that here's just a simulation to show how we do it, how we perform the experiment. So if we turn on the system, there is a loss inside the system. So the system will automatically reach one of the stable state, as you can see here, the VA and the VB. And then at this point, we turn on the singular, the arbitrary wave function, this waveform generator to input an excitation or drive signal to the system. As you will see that after we add the drive signal, it will reach another stable state, and then we release the drive signal, which means we turn off the waveform generator. The system will evolve into another stable state. So to compare that, we will see to say that this state 1 and state 2 are different. We can say from the ratio of VA over VB. At first, VA over VB is larger than 1, and then for state 2 is smaller than 1. And we can also look at the eigenfrequency. It's 78.6 here, and it's 67.7 here. So we know for sure that there are two states. So the idea to reach two of the bistable state is that we add a driving signal. If we choose drive signal correctly, we can jump from one state to another state. And then for the gain setup in our system, as we said before, we use a 2-diode. Here we show the resistance of this 2-diode. You will see that it's a monotonic decreasing function, which means that then this monotonic decreasing function will give us the resistance. Ideally, for an ideal amplifier, here we have an analytical form. It will give us the resistance as function of the input. Here, the V1 here. And so for a real system, for a real circular system, it's not ideal. So we need to measure the resistance, the elective resistance, as a function of the wave amplitude. So what we do is that here's also a simulation. We do it in the we do a similar measurement in the experiment. So we turn on the system. The system is we turn on system or the amplifier. It will start to reach a stable state, and then we change this resistance, and then this V1 also change. The idea is that this resistance, when the system reaches a stable state, this positive resistance equal to negative resistance. So then we measure the resistance of this resistor. We can get the negative resistance as a function of V1, and here is we show. And then we change to the gain coefficient. We transform to the gain coefficient, and then we can have the gain as a function of voltage. Here the V1 here, and here's the data. This is the data point, and we can fit this data point smoothly with this function. And so and then we obtain the gain as a function of phi A inside the system with this and A, B, C are the fitting coefficient. So in other words, now we have the gain coefficient for real circular system. We need to say that actually this gain coefficient, the dependence on the wave function is different from the typical gain model inside the in the optics. However, the difference between this gain model doesn't change the physics in our system. The eigenspectrum of the system do not depend on this either this gain or this gain we use in our experiment. So if you you want to do an experiment in optics, you will typically use this gain model, and the eigenspectrum is the same. So then we can measure, after all the techniques we said before, we can now measure the resonant frequency of these two modes as function of the LA. LA is the variable inductor, and resistance of the second resonator, or the loss coefficient. And we can measure the resonant frequency, and also the ratio between VA and VB, which is the wave amplitude. And also we can measure the phase delay between VA and VB. So we can measure the eigenstate of the system. And then we can do a transformation, also transfer back to the frequency and return it to fit our model. And we can see that actually the measured data fit well with our model. And here, in the reality, the error bar is very small. Here for demonstration, we actually increased the error bar by around 10s or 100 times. So the error is inside for this measurement is very small, to show that we increase its amplitude by around 100 times. So in reality, you cannot see this error. We can fit the slope of our measurement is fit well with 1/2 and 1/3. So that's our experiment, and then we will talk about why we are interested in in this system. So we want to do that. We want to introduce some applications, potential applications associated. Actually, it's associated with the excitement point. I will show that our nonlinear excitement point actually keep all the key features of the excitement point, and so we will say maybe our nonlinear excitement point can realize the potential applications associated with the excitement point. So that's our idea. So the first application we want to discuss about the enhanced sensing. The idea is actually quite simple. As you look at this point, these are two famous papers in 2017, and they say that if we put our system, if we turn our system to the excitement point, and then a very small change of system parameter will introduce a very large change of the eigenfrequency. And then if you measure the eigenfrequency, you will feel the change of the system. So which means that the system is very sensitive to the change of the environment. Or in other words, we can use the excitement points for the sensing. So they say that to calibrate the sensitivity of the system, they use this the resonant frequency, the change of resonant frequency over the change of the external parameters. You will see that it diverges as we approach the excitement point. And for higher order excitement point, it diverges even faster. That's why they put a lot of effort to realize a higher order excitement point. So it seems to realize that once we have the excitement point, we can have a very sensitive point, and then we can use it for to measure a very small singular. However, there is an ongoing debate on the EP related sensing. They say that actually the two papers, two later papers, what the two later papers talk about is just the transduction coefficient. For the sensitivity in the typical textbook, we need also to consider if we can measure the frequency. Say here m is the frequency. Really, if we can measure the frequency precisely in the reality, because there is noise, so there is a finite bandwidth for the signal. So the smallest measurable change of the system is delta. The delta omega, delta m is the resonant frequency over the partial omega, partial epsilon. And then there is quite a few papers talking about this. If we choose this as the definition of sensitivity, then there might not be sensitivity enhancement near the excitation point. Here we choose one of the papers from Professor Renbao Liu's group. And in this paper, they say that actually there is in quantum information, they have a famous formula which they call the quantum CR bond. In this bond, they say that this ratio, the sensitivity, is large or equal than 1 over f. F is quantum Fisher information. And also with this two resonant system, they calculate this EP2 system, they calculate the quantum Fisher information. So if there is an enhancement of the sensitivity, then F should be large, and then this can be very small. This can be very small, and then correspond to very high sensitivity. However, they say that for the quantum Fisher information, as they approach the excitation point, there's no peak here, which means that there's no enhancement of F. So here this ratio is not enhanced near the sensitivity defined here is not enhanced near the excitation point. So so you may say that that's only for EP2. How about higher order excitation point? So here we do a simple calculation for an EP3. The line width, which is also calibrated with the PF factor, Peterman factor, with PF factor, for the linear case, which is proportional for this EP3. Linear EP3 is proportional to delta omega, the determining to the 4 over third, and the singular enhancement factor, which is partial omega, partial determining, which is also to the delta omega to the 4 over third. So the singular to noise ratio or the sensitivity, which is SEF over PF, which is of order delta omega to the order 0, which means that there's no enhancement if we follow this definition for the sensitivity. However, if we now look at our exceptional NEP3, the nonlinear exceptional point, we will see that here the singular enhancement factor is the same as before, because the eigenspectrum is the same as before. However, if we look at the PF factor, now is proportional to, instead of delta omega to the 4 over third, is only 2 over third. So the singular to noise ratio now is delta omega to the 1 over third. So when the determinant delta omega go to 0, this singular to noise ratio diverge. Or in other words, singular to noise ratio -1 go to 0. Here we show the singular to noise ratio we calculate for a linear system. For linear EP3, sorry, I forgot it's EP3 or EP2. Anyway, it also EP2, both EP2 and EP3 will converge at this excitation point. However, for our EX here, the EP3, NEP3, it will vanish. So which means that even for this system, for our NEP3, we will have a diverged sensitivity. And then let's so And if we look at the real experiment measurement, actually we are looking at the dynamics, and there is another advantage. We should say compare our system with the traditional linear system. You will see that here for linear system, if there's low noise, the amplitude of the wave function will, because as we slightly change the system parameter, it will go to the gain or loss mode, and the wave amplitude will either exponentially increase or decrease, and then after a short time it will reach the measuring the bound of the instrument, which means that we have only a very a limited time regime for the measurement. However, for our satural gain system, the wave amplitude is stable. The mode is stable, which means the wave amplitude doesn't change much as the time goes. So which means, or in other words, we can measure the signal as long as we need, and then we can have a very precise frequency measurement. And here is and so for real measurement, actually we can change here. We also introduce noise. For the linear system, it will also the expression the signal will exponentially increase, and for our system, we will see that the noise, even with this very large signal, the noise is greatly depressed, and this depressed noise is actually due to the feedback mechanism of the nonlinear satural gain. And here to show that, we can show the feedback effect mechanism of this within this simulation. As for here, as we turn off the excitation, the system is not at a stable state, and then as this stable state will be a traction point inside the parameter space, and then it will track the system back to its stable state. In other words, this attraction inside the parameter space will offer the feedback mechanism, which is suppressed noise, and this mechanism this mechanism further suppresses noise. And then, so for short summary of our system, and so inside our system, even though the PI factor diverged, the signal to noise ratio diverged faster. The signal to enhancement effect diverged relatively faster, so the signal to noise ratio still diverge for our system. And there is also feedback mechanism further suppress the noise inside our system. So here, this is the signal to noise ratio we measure in our circular experiment. It varies at the acceptance point and the EX point, as we show here. So here we use, if we look at this point, our paper, you will see that here the PI factor still diverge. Then we ask ourselves, is it possible to have a system that the PI factor is not diverge? So this is the question we ask. And then if we want to ask this question, we need to go back to the difference between a linear system and a nonlinear system. So for a linear system, what we can do is that we can solve the eigenfrequency and eigenmodes, and then we can decompose an initial state to a combination of the eigenmodes, and then the final state is the evolution combination of the evolution of each state independently, and then we can get the final state. However, if we look at the nonlinear Hamiltonian, the picture is different. For the nonlinear Hamiltonian, of course, we can also solve the eigen equation as we have done before, and then of course we can also decompose the initial state to a combination of the eigenstate. However, the final state here is different. The final state is not a combination of the evolution of each eigenstate. What we do in the simulation is that we actually can only perform the dynamics with the nonlinear Hamiltonian in time. And the idea is that for because the Hamiltonian actually depends on the eigenstate. So if we choose one of the eigenstate, then this Hamiltonian is here is anchored by this state. It cannot, for different eigenstate, the Hamiltonian is different. A system can only support one Hamiltonian. So in other words, if we choose one of the eigenstate, the system Hamiltonian or the gain coefficient is fixed by this state, and then the dynamics of a system is governed by the Hamiltonian, which is fixed, which is anchored by the state. So then, with this in mind, we can now design a system which now is possible to design a system. So for our previous case, as we already said before, the PI factor diverge. How about, so the first thing we do is that we increase the system. Here we include another resonator, and we said that this resonator have a linear gain. And you may wonder why we have a separate gain here, a linear gain here. Is it possible? The answer is yes, that if the gain has a separate, the idea is that we suppose that this system has a stable state where the wave amplitude in resonance C is much smaller than the satural value of this gain. Then this gain can be safely regarded as in the linear regime. So with this model, we can now we can prove for general conclusion that if we have n resonators, the highest order of nonlinear acceptance point is 2n minus 1. So for n equal to 3, the highest order of acceptance point is NEP5. For n equal to 4, the highest order of nonlinear acceptance point is 7. And then for 5 is 9. So for a similar case, we consider 3 resonators. So now we can have an NEP5. We can say the eigenstate for the eigenequation, the nonlinear eigenequation, the eigenstate merge into this point. And of course, the ratio change is one of the critical behavior of eigenspectrum is 1/5. And now we look at this. Okay, sorry. Now we will show that actually for the dynamics, we said before, the Hamiltonian is for the dynamics, the system will soon reach one of its stable state. After it reaches its stable state, the system Hamiltonian will be fixed by this state, will be anchored by this state, and then the gain coefficient is almost fixed, and then we can have a instantaneous Hamiltonian, which governs the dynamics of the system. So for this instantaneous Hamiltonian, we can say that we will show that the eigenbasis is complete. So to show that, we define 2 functions, which is here chi, we use it to calibrate the orthogonalities and the PI factors. And for comparison, we'll also introduce a linear system which process EP5, which is a linear system. So for chi, for the Hermitian case, here the only 2 eigenvectors are orthogonal to each other. So this one is 0. So the chi is 1, which is for Hermitian case is always 1. And for EP5, here phi A and phi B, there is no is equal to 1. So the 1 minus 1 is 0. For the EP5 inside the linear system is values for the chi. However, for our NEP5, as the basis is complete, so it's a finite value, and this can also be seen from the PI factor. And you say that for EP5, this linear system, it diverge, the PI factor diverge, and for our linear system, the PI factor is a finite value. And also we can show that for linear, we can also calculate the eigenvalues and the eigenstate for the instantaneous Hamiltonian. We say that these 3 eigenvalues of the instantaneous Hamiltonian is a 3 by 3, as we it's a 3×3 Hamiltonian. It's an instantaneous Hamiltonian 3×3, and its eigenvalue does not converge to a point, and also its eigenvector its eigenvectors do not collapse. So this is a NP5 for the self-consistent solutions. However, for dynamics, is governed by the instantaneous Hamiltonian. The eigenbasis of instantaneous Hamiltonian is complete. So once we have this idea, we won't say that it's I've got to show the advantage of the of why we are interested in a complete basis. So we go to another quite famous applications of the EP5 of the excitement point, which is a carrier state transfer. As the carrier state transfer said that if we start with one of the state, we will go to a circle. Here's the excitement point. We go circle around the excitement point. The final state actually only depends on the direction of how we're circling around this excitement point. If we go clockwise, anti-clockwise, it go to the upper one, and if we go clockwise, it go to the lower state. So the final state only depends on the direction of how we circling around this excitement point, and use this fact we can design carrier state transfer. We say that from right hand side, if we input these two signal, we have this blue signal, and for fundamental mode, and if we insert these two signal, we will have the higher order signal. So the state so the final state depends on how we circling around this system. And now in the real system, there must be noise, and if there's noise, as we said before, near close to this excitement point, the two eigenvector becomes parallel to each other. Then a very small noise will change will have the system jump from one to another one. So then the carrier state transfer cannot be seen inside the system. Later, we'll show the effect as we introduce noise inside the system. And here we show that for our AP5, we can also have a carrier state transfer. The carrier state transfer depends on how we go clockwise. For here, if we go clockwise, we'll see that it go to the lower state, the state on lower level. And if we go clockwise, it will jump here, and then it will go to the state on the upper level. So it's also the final state only depends on how it go clockwise or anti-clockwise. And here's the simulation without with the noise. And here's the solid one is a simulation without noise. And with the noise, we'll see the signal will vibrate around this the signal with noise. And so for comparison, we also introduced EP2. And for as in the literature, we can define a quadratic function lambda, which ideally is 1 to calibrate the carrier state transfer, how well the system can keep the carrier state transfer. And also we measure we can simulate the standard deviation of the quadratic function lambda in the presence of noise. And here for the traditional excitement point EP2, you will see that as we decrease the radius, the lambda will deviate from -1 very quickly. Here is 0.3. And you may ask, can we go away very far away from the excitement point? The idea is also difficult for the experimental implication. The reason is that as you go away from the excitement point, you will need a lot of time to go around this circling. So as in the real experiment, it's difficult to implement the gain. So which means they are all lossy mode. And then after you go from here to here, the signal will be very, very small. I vaguely remember that for this experiment, the dip is around -40 dB for the signal. So we need to go close to this excitation point, but not that close. So here we see that if you go close to this excitation point, the noise will be unusual. It will deviate. The lambda will deviate from -1 very quickly. However, as with this complete basis and the feedback mechanism of our system, you will see that this lambda will deviate from -1 very slowly. Here is 0.01. You will see that at this point, when the radius, the circling, the radius is very, very small, it starts to deviate from -1. And also for the standard deviation, it converged here. Here is diverged near the excitation point. And for our case, the standard deviation of this lambda converge, as you can show here, as you can see here. So we won't say that a complete basis indeed help to keep the dynamics stable in the presence of noise near the excitation point, which is very important for the real applications. So that's all for the theoretical purpose. So then we ask ourselves, can we really realize this kind of EP5 in the experiment? Actually, it's very difficult for the EP5. There are two reasons. The first is that even though now we have nonlinear mechanism, the parameter is reduced quite largely. However, we still need to turn. In our case, I guess it's 7 parameters, or 5 or 7. It's still a lot of parameters need to turn. This is one point. The other point is that NEP5, near the NEP5, the eigenfrequency change is very sensitive, which means that a very small change of the parameters will deviate ourselves far away from the NP5. So, in other words, the NP5 is too sensitive to reach. So it's a kind of a disaster for the experiment for the experimental implication if we want to consider an NP5. So, in other words, we have to decrease the order of the nonlinear excitation point in order to realize it in the real experiment. So as we already said before, the first proposal we have the NP3 is the basis is not complete. So we need to change the system. Now then we ask ourselves, if we turn this coupling to make it non-Hermitian, here the non-Hermitian will mean that here kappa plus and kappa minus are not complex conjugate. Is for simplicity we set it equal to kappa 0 plus I kappa v. If kappa v is not 0, if kappa mu is not 0, then this is not Hermitian. We call it non-Hermitian. It's not necessarily non-reciprocal. It's just non-Hermitian. This non-Hermitian coupling can be easily realized with this waveguide, lossy waveguide, or this system. And then with this model, we can realize a nonlinear excitation point with a complete basis. So for this coupling, it actually can be easily realized with this capacitor, which we already said before, plus resistor. So it's very simple. We only introduce a loss. While we introduce the coupling, we can introduce a loss term in the coupling. And this loss term, with this simple coupler, we can realize the non-Hermitian coupling required in our model. Same as before, this is we can measure the VA and VB. We can measure the eigenfrequency. We can match it with our model. We see that we can see that the PF factor does not diverge here, and we can see the single to noise ratio to -1 go to 0, or the single topology ratio diverge near our NEP5, NEP third, and we can see that the two eigenstates of the instantaneous Hamiltonian does not collapse. For here we see that here's the NEP3. You will see that this gray curve and this red curve does not collapse to the same point, and this means that for all the points, all the parameters we here the epsilon, there's no such point that these two eigenstates collapse. So we can know that the basis is complete. So for the summary of our talk, inside this talk, we introduced the concept of a nonlinear excitement point. We won't say that actually the unstable state contribute to the topology and the dimension of the system. It changed the orders of the nonlinear excitement point. And with this unstable state, the nonlinear excitement point requires much less parameters to reach, compared with the regular linear excitement point with the same order. There is an advantage of our nonlinear excitement point. It keeps almost all the key features of the excitement point, say like the divergent spectrum response, and also the chiral state transfer near the excitement point. And beside that, there is a feedback mechanism which suppress the noise inside the system. And also we can have a complete basis, which indicate a converged noise near the excitement point. So the noise, which is an issue for the traditional linear excitement point, is not an issue for our nonlinear excitement point, which means that the application associated, the potential application associated with the linear excitement point will almost be easily transferred to our nonlinear excitement point, and the noise there inside linear system is not an issue for our nonlinear excitement point. And here's our reference. Okay, I guess that's all for my talk. Thank you for attention.
Yeah, thank you, Professor Meng, for the very interesting talk. So, dear colleagues, do you have any questions to him? Yeah, I see the hand from Nikita Lechna.
So the manual hand. Yeah, dear Meng, thank you for a very interesting talk.
And thank you.
I have something like 5 questions. So Dima, how should we arrange? Can I ask them all at once, or we can mix them somehow?
So I think actually maybe it's better if you ask consequently. Yeah, one, then answer, then again. Okay.
Sure.
All right. So can you please switch to slide 6 when you talk about dimensional reduction? So okay. I wonder if there is truly sort of precise mapping, or there are some limitations and bonds, for example, for this nonlinear parameters.
You mean on this one, or page 9? You mean this one?
Yeah, this one probably.
Okay.
So as I understand, in a nonlinear case, we might obtain some additional bonds, for example, on coupling coefficients or on our freedom to tune some parameters. So can we obtain pure mapping without any additional limitations, or they're unnecessary in any realistic situations, for example, for experiments?
Sorry, can you? I do not hear the question very clearly. Can you say it once again?
Yeah, I mean, is there a precise mapping in arbitrary situation, or we have some additional limitations when mapping a high-dimensional linear system to a lower-dimensional nonlinear one?
Oh yeah. Here, for this mapping, we only require that. Actually, as you can see here, we require that the phi A and phi B for the linear system is the same as this. Sorry, psi A, psi B is the same as the linear system, and then we will require that the linear system after mapping, the eigenstate of the linear system should be normalized, which is nature, and should be orthogonal because it's a nonlinear system, so it should be orthogonal. So with this two requirements, which we have, then we have 6 equations. And with these 6 equations, the mapping is 1-to-1, which means that there's if the requirement is as we said before, as I just said, then this mapping is 1-to-1. There is no additional freedom. Do I answer your question?
Yeah, okay, thank you. And also I have a set of questions for the circuits part, something like page 13 and the following slides. Yeah, so why have you chosen this frequency range of something around 70 kilohertz?
Actually, we do not have a preference for the frequency range. The frequency range just we choose the inductor and the capacitor, which is very common in the industry. So we just buy this to the capacitor and the inductor, and for our own system, we can have this variable inductor, which is the inductance is of the same order as this one. So that's basically how we choose the resonant frequency. So we do not have a preference for resonant frequency. Just for demonstration, we choose the inductance of this one close to this one. So that's why we have a resonant frequency around 7.8.6. If you can turn the inductance or the capacitor in the other range, you can easily turn the resonant frequency. It doesn't matter much.
Yeah, thanks. So at our faculty, we have experimented a lot with topological electrical circuits, realizing various Hamiltonians, and we struggled with somehow optimizing the equality factor, which imposed some limitations on our values of inductances and capacitors. And also, what is the form of excitation which you apply here from a signal generator?
I understand your point about the if we look at the topological circuit, we need to choose a good inductor capacitor. In our case, we do not have that concern because I guess it's one of the reasons is that we have a gain here in our system, and the loss is that we do not need to care that much about the Q factor of the system. So that's why we are not we do not need to be careful with the resonant frequency. And for your question, the third question, actually in our system, here excitation means that as you can see here, we have the waveform generator. There's a probe. We can put the probe onto one of the load here, maybe some here, and then we input we turn on the waveform generator, and then it will enforce a single voltage difference between this point and this point, which will change the system. And or in other words, it will drive the system to another stable state. This is a simulation, but it shows basically what we do in the experiment. So when we turn on the waveform generator, we'll see that the system will reach one of another stable state. It's not a two stable state of our eigenspectrum because here we have the waveform generator, but it's one of a stable state. And then here we just turn off the waveform generator, and then it will draw back to one of the stable state.
Yeah, thanks. And also, I wonder if there are any frequency dependence in the negative resistance in this part of circuit.
It's a very nice question. We measure the frequency dependence of the system is very small. I guess I vaguely remember. I don't have the data here, but I vaguely remember is less than 1% in the frequency range of interest. Actually, the nonlinear effect depends. The nonlinear effect mostly come from the dependence of the inductance or the capacitor on the wave amplitude. So for the frequency dependence is very small in our case. I guess the reason for this is that we are actually looking at a very low frequency. It's much lower than the frequency, the frequency upper limit of the amplifier, around megahertz, I guess, 10 megahertz or very larger than this one. So the frequency dependence of the system is, of the elective resistance is very small in our case.
Yeah,
So-
this
so-
was a
sorry.
good point about working in kilohertz range, because at gigahertz frequencies, I think it can be quite hard to obtain some non-dispersive behavior for such negative components. Yeah, sorry, Dima.
Yeah, can I also add questions here as we are? Can you please go back on the previous slide?
This one?
Well, yeah. So here you have a scheme of the negative resistance. Usually, such non-Foster elements quite unstable. Yeah, and and usually there is only small frequency range when you can obtain such negative resistance. Did you somehow estimate maybe in simulations or tune it to some resonant frequencies before you realize it in experiments?
Actually, I'm not quite sure about when the elective resistance will be unstable. In our measurement, is quite maybe the reason I guess is similar as I guess is same because we are looking actually a frequency, a working frequency, much lower than the frequency. The structural frequency limit of the amplifier, so it seems quite stable in our setup from our measurement experience. Maybe if we increase the frequency, say like for 1,000 times, then the electric resistance will be unstable. And here, there's another reason. Here we also, instead of a separate gain introduced by this amplifier, we introduce a two diode component, which to control, actually this helps us to control the elective resistance. In other words, the voltage here is lower than the upper limit of the amplifier. This might be another reason. I only can say that in our experimental measurement, the elective resistance seems to be stable. I'm not sure whether if we increase the wave amplitude, the amplitude, or if we increase the working frequency, it will be unstable.
Okay, thank you. Nikita,
Okay, thank
please.
you. Very nice
Go on.
question.
Yeah, I have also just finished with this technical radio frequency part, and I have a couple more general questions. So somewhere in the vicinity of slide 19 or 20, yeah, about applications. Yeah, you mentioned this quantum bond. So I'm not a specialist in exceptional points at all, but it looks interesting for me. What happens if we consider the quantum scenario, for example, with single photons? In this case, of course, we have some considerable dephasing and decoherence because of losses in the system, but we still can implement some gain, probably with individual quantum dots. So what particularly happens with entangled quantum states when we cross the exceptional point? Is the entanglement preserved? Can we somehow use this to lower the noise limit as well?
Actually, it's a very nice question. I cannot answer this one. I myself, I don't know quite sure about whether the entanglement will be preserved or will be changed or something else near the exception point. I only quote this formula from the Professor Liu, who is an expert in quantum information. So in their work, they have this formula. With this formula, we can show that the quantification information, which is maximum information you can obtain from a system, and then so if this is nudge, then there's a sensitivity enhancement. And I say for how they realize the gain, I'm not sure. Actually, I read a few papers, but it's not that simple. I don't know how they can be treated standard in terms of the gain or the loss inside the quantum system if we consider a single photon or an entangled photon or two entangled photon. I'm not sure. They for this paper they only cares about they say that if they can have this Hamiltonian, they must have this bound, and then with this bound they perform this simulation and show that there's no enhancement for the traditional linear excitation point. And for your question, the main part of your question, I'm not sure. It's a real life question. I just don't know the answer.
Yeah, I believe this question can actually turn out to be something unknown. So it's just an idea that came to my mind. So also regarding the Hamiltonian, which you consider throughout your talk, so you mentioned nonlinearity only in one of the diagonal terms. Will there be some specific differences if we add nonlinearity to the off-diagonal terms? So a sort of nonlinear coupling, which also can be implemented, for example, in optics.
Sure. Yeah, it's a very nice question. Actually, I personally, I think it's very interesting to add a nonlinear term on the off-diagonal, the off-diagonal term. I'm not sure about the result, but I guess the picture we talk about is quite general. The picture said that if we have nonlinearity, which can introduce okay, maybe this I should. Oh yeah, looking at this figure. If we, can you see my mouse?
Yeah.
Oh, okay. Oh, sure. Great. So yeah, if we have nonlinearity, which help us introduce additional modes, then we can have higher order excitation point. That's the basic idea we want to say. Here, the linearity introduced by sexual gain introduce another mode, and then we can have a NEP3 inside a two resonator system. So if the nonlinear term on the off-diagonal, the off-diagonal nonlinear term can introduce another modes or this S-shaped curve, then we can also have similar physics. I mean by the high order excitation point, or maybe an excitation point with a complete basis. I'm not sure about this part, but if you have additional modes, you might have the possibility to have higher order excitation point inside the system.
Okay, yes. So the point is to maximize the degree of nonlinearity of the exceptional point, as I understand. The higher the better in terms of this very rapid slope, for example, for sensitivity applications.
Yeah.
Yeah, thank you.
Yeah, it actually preserved the slope of the traditional excitation point, but on the other hand, it also suppresses the noise for a great amount. So we want to argue that is suitable for applications. Yeah, thank you.
Yeah, and finally, regarding the noise, slide something like 20 or 22. Yeah, when you consider the addition of noise to the system. So what is the spectral density of this noise? Is it some sort of white noise or pink noise?
It's a simple white noise. This is a very nice question. We do not look into details of the spectrum of the noise. We just add the simplest case, the white noise. Yeah, it actually the spectrum of suppression for the noise is very broad in our case. So it doesn't matter much what the spectrum noise.
Yeah, that's nice. And as I understand from slide 28, with such an idea, we can implement something like a photonic diode if we add some additional pump.
You mean the third
the next
model?
one? Yeah.
This one?
In this case, the previous one.
Oh, the previous one.
When we consider chiral states with some mixed fundamental and high order mod. So as I understand, we can then develop some device which acts as a sort of a photonic diode, but requires some additional ambient lighting, for example, from one and another side.
Yeah, maybe in their paper they won't ask. They try to argue that it's a long reciprocal, but not the typical long reciprocal inside in the literature. The phenomenon is, as you say, is similar like the diode, but not a real diode.
Are there any detailed simulations or experimental demonstrations for such jumps from one loop to the other one for another exception point?
This is a simulation for the toy Hamiltonian, the Hamiltonian we use, and for a circular system, I do not remember. I do not remember whether we performed the simulation, but I think the simulation will be easy to transfer to a real circular system. So if you can design a similar physics within this waveguide, I think we can do the similar simulation within this waveguide system. I mean, the Hamiltonian described the wave propagation along this waveguide is similar as our case. The physics should be similar, and the simulation should be transferred to here, I guess.
Okay, thank you one more time for your answers and very interesting talk. I think I've asked all my questions.
Thank you,
Nikita. We have also a question from Alexey Dmitriev.
Also, I would like to thank you for the talk. I'm sorry, can you hear me?
Sure.
Yeah, okay. So I have a question about the completeness of the exceptional point basis, the NEP5. So you have shown on the slide concerning the completeness of the basis, the metric of orthogonality. So I see you here consider the two states, psi alpha and psi beta. I'm afraid I can't understand what do they mean.
Here alpha and beta just run from 1 to 5, and we here this line for on average.
So you average this production for every pair of states. Do I get that right?
Yes. Yeah.
Oh, okay. Now I understand. So because I thought you just took two states, considered them, and how that was supposed to evaluate the completeness. Yeah, if you cycle through them all, then okay, I understand that should work. Thank you for the answer.
Sorry for that. I forgot to explain this to subscribe. Yeah.
Okay, thank you. So I have also a few questions. The first one is regarding the SNR mechanism. Can you please tell me what is the mechanism of SNR enhancement? As far as I remember, it's slide number, I don't know, 20.
You mean signal enhancement?
Yeah, signal to noise ratio enhancement, yes.
Yeah. Here, signal to noise enhancement in our case actually depends on two factors. Yeah, the first, we define signal to noise ratio, which is typical in the literature, which is a signal enhancement factor over the PF factor. PF factor basically reflects the line width of the system. So if the line width is very broad, we cannot measure the signal very precise. Then the signal to noise ratio is small, is no. And a signal enhancement factor, which means that a change of the external parameter will change the frequency. Here, we in our system, we assume we are measuring the eigenfrequency. So the change of eigenfrequency relative to the change of the external parameter. And the signal to noise ratio is this SEF over PF. And we know that close to when we approach an acceptance point or NEP, this one will diverge. Say like we have the EP3, it will diverge as we determine go to 0. It will diverge over of delta omega to the -4/3. So if this PF is finite, in our case, for the first NEP5 model, the PF diverge as delta omega to the -2/3. So as a result, the signal to noise ratio diverge to delta omega, the determinant to the -1/3. So it still diverge here and for the two later case, the PF is finite and the signal to noise ratio still diverge. So the SEF still diverge for the later two case. And so we know that the signal to noise ratio diverge for our case.
Okay, so by the way, does it mean that if the noise will be comparable with a signal, you can reduce the noise and amplify the signal, and you can retrieve the signal, even if the noise is comparable or even higher than the signal?
Yes. In the real, actually in the experiment, I guess the answer is yes. In the experiment, they consider it's because the noise must be there because there is a fluctuation dissipation theory, which means that if there's a noise, there's a noise, and then we cannot control. Actually, we cannot control the amplitude of the noise. So they say that what they consider is the minimal signal they can measure. So if the signal is very small, we need to suppress the noise in order to measure the signal. That's the idea of signal to noise ratio in that setup, I guess. So for your question, I guess if the signal is comparable with the noise, if we can, in our case, we can suppress the noise, then we can have a better measurement of the signal.
Okay, thanks. And another questions. Can you please go back on the slide number 6?
Number 6. Yeah.
Yeah. So here, yes. So here you told that the topological invariant can change depending on the way you calculate it.
Yes.
Yes. So what does it mean in practically? So usually topological invariance, for example, estimates how many topological edge states will be on the boundary. Yeah. But here, if you have a system and you calculate differently the invariant, you can obtain completely different results. What does it mean practically?
Yeah. For firstly, that here the topological number defined here cannot be directly transferred to the edge state. inside this system, because it's just inside the parameter space. There's no periodic system and no bulk boundary correspondence for this case. So, but your question still exists: how we can change from say the Wanding number 1/3 to the Wanding number 1/2. The answer is that as we slightly change the loop, we're circling around the acceptance point. Actually, there is a something jump. I cannot describe it clearly. There's no we should say the continuous way of turning from one loop to another loop. So there must be a jump. So we previously we say that the topology charge should be the same. Is that we have the two loops can be continuously turned to one other. However, for this case, in their paper, there's no continuous transformation between two loops. So basically, the one loop is along the XY direction, the other loop is along the YZ direction. So and then we cannot continuously turn from one to another one.
Yeah. Okay. Yeah. Thanks.
I cannot explain it clearly. Maybe you can look at this paper.
Yeah.
They
Sure,
have better illustrations. Sorry.
No problem. I think I got it actually. Yeah. So, dear colleagues, do you have any other questions? So if not, I'd like to thank our speaker again. Yeah, and we would like to invite you again to our seminars. Actually, the seminars are weekly. If you are interested in, you can also join us just as a not as a speaker,
great,
but as a listener. Yeah.
That's
Okay.
great.
Yeah. Thank you very much.
And thank you. Thank you for listening.
Goodbye.
Yeah, thank you. Bye.